Hello class, welcome to the online lecture modules that will cover the Laplace transform technique as we apply it to process control. This material pertains to chapter 3 in your textbook, and I encourage you to keep these online lectures as a reference as we move throughout the course. So I want to start by talking a little bit about Laplace transforms. We've all seen Laplace transforms in our introductory differential equations course process analysis. So we know it has some utility in solving differential equations. What we didn't really see in those applications is how useful it can be for solving dynamic problems. That means that there's a derivative with respect to time showing up in these problems. So Laplace transforms can be used to develop transfer functions, which is a specific terminology we use a lot in process control, and they're very convenient and meaningful to represent the input versus the output behavior of a linear process. Laplace transforms and transfer functions are both going to provide insight into the behavior of dynamic systems, and this will be really important in the process control field. So you may or may not remember that if we have some function f of t, we can take the Laplace transform of that function by taking this indefinite integral from 0 to infinity of that function multiplied by the exponential of negative st with respect to time. Here s is the Laplace transform variable, and it refers to frequency. Okay, when we transform this function, we'll use some more terminology. So after it's transformed, we'll see that form go from f of t to capital F of s, where now our variable is s, the transform variable. Conversely, when we do, we'll transform into the frequency domain, do some algebra, and then we'll want to understand how our function looks in the time domain. That's, the time domain is where we do most of our understanding of these dynamic processes. So we'll want to inverse transform back into the time domain. So typically this has to be done using Laplace transform tables. You could find more complete versions of the Laplace transform table in any differential equation book, especially the Kreisig differential equation text we use for process analysis. However, our process control book contains some tables that should be complete enough to use for virtually any process control application we'll encounter within this course. Okay, so I just want to emphasize that Laplace transform are a standard notation in dynamics and control. They will make our life a lot easier in that they're a lot shorter to write out than all these formulas. They're going to convert some sort of differential equation into an algebraic equation, which can be manipulated much more easily and is a very robust technique. This is also very advantageous for block diagram analysis. So we've talked a little bit about block diagram analysis, but as we get into more sophisticated analysis of process control system, we'll draw loops as blocks where we can use these transfer functions, so something we find in the Laplace transform domain, to represent the individual components of a process control system within the loop. Okay, so typically we see that Laplace transform, they're a very useful tool. We need to, sharpen this tool and refine it so that you're ready to utilize it as we encounter problems in process control. So typically we're going to use Laplace transforms to find the solution of differential equations. Okay, so let's say we have some function where the derivative of y is some kind of function of y. Well, we can use Laplace transforms to solve for y as a function of t. Okay, so also we can use Laplace transform to analyze our control system. So as we put together these control loops, we can use Laplace transform transfer functions to analyze the response of these systems. And of course, by taking the inverse transform of these results, we can also find the transient responses for different inputs as functions of time. So I just want to kind of look at this process within a flow chart. So what can we do? Well, we have two domains. We have our natural domain. We're used to thinking about the time domain, which has a independent variable of time. And we can use Laplace transforms to shift into this frequency domain, where the independent variable we're talking about is s, which corresponds to frequency. So what we know is that based on first principles, we can develop some sort of ordinary differential equation in the time domain, some sort of initial conditions based on the constraints of our systems. We can use Laplace transforms to take these from the time domain to the Laplace domain. Okay, now instead of having a differential equation, we'll have an algebraic equation, algebra, right? Everyone likes algebra better than solving differential equations, I bet. So next we'll be able to do some manipulations, and we could find that there's some function that we can determine as the ratio of the input to output. Okay, so right here, this is very important because this function, y of s, is our transfer function. So we're going to use this term. All right, so after we have our transfer function, we may have to do some manipulation before we can go back into the time domain. Remember, we may be able to solve our dynamic system for the direct time-dependent function y of t. However, we need to take the inverse transform. So this is typically done by using a Laplace transform table. However, some algebraic manipulation may need to happen. This algebraic manipulation may include partial fraction expansion or decomposition. They can be used interchangeably. So we'll do a little bit of review of that. Remember that term is an algebraic operation. You likely learned this back in high school, maybe even 8th grade. So dust off those dusty brains and we'll get to work. See you in the next video.